William Knowles discovered in 1968 a novel way to carry out asymmetric hydrogenation reactions of organic molecules by using a catalyst molecule, namely a chiral rhodium metal complex. As research director at the Monsanto pharmaceutical company, he used this discovery to develop a process for producing an amino acid, dopa, in pure form, in pure L form. And L-dopa is today a very important drug against Parkinson's disease. William Knowles' work pioneered a whole field, asymmetric catalytic synthesis, and his title of his Nobel lecture is Asymmetric Hydrogenations. And I look very much forward to listening to this. Welcome to the floor.
I guess this is on now, yeah. I never expected my research, you can never tell where a research program will lead, but I never expected mine to lead me to this podium. I thought before I'd begin the lecture, I'd share with you a couple of cartoons that people have sent me in congratulatory letters. The first of these is a grin and bear it cartoon that occurs frequently in US newspapers. And this is a very old, maybe it's 20, 30 years old, but I think it's quite pertinent. So try the next. This is a grin and bear it cartoon, and I think all of you can read the caption. Now the second cartoon is a more modern cartoon. This is done by a children's book illustrator, Quentin Blake in London. And he's explaining to his friend what is meant by the difference in these chiral molecules. This is the next one. If you can't read this, it's, "Dear Bonnie, thank goodness you came to me for enlightenment." And he said, well, this is a right-handed chiral enantiomer. This is a left-handed chiral enantiomer. As you can see, they're quite different. I hope everything is clear now. We'll shut the lights off for a minute. Well, actually, my account today is going to be the story of the genesis of an invention. And I think the inventive process is really not very clearly understood. But one factor that seems to be important is to have a fairly heavy infusion of naivety. And that's why I think so frequently the experts don't do the inventing, but they're the ones who come in once the lead is established and exploit the area. Our work is an excellent example of this type of phenomenon. In the study of these life sciences, chiral compounds are important, any life sciences. And in the past, when chiral compounds were needed, chemists had to resort to biochemical processes or make racemic mixtures and then separate them with elaborate resolution procedures. Industry, the problem is particularly severe since resolution with its numerous recycle loops and fractional crystallization is inherently expensive. Thus, large volume products like monosodium glutamate, lysine, and menthol are traditionally made by biochemical routes, even though there are direct chemical procedures for their racemic forms are readily available. We became particularly aware of this in the early 1960s. We were making a paper evaluation of a monosodium glutamate process. We got the racemic mixture, the DL mixture, easily, but by the time we'd resolved, the costs had doubled, even though we used all kinds of recycle back the unwanted D-isomer and all. We had all kinds of special things put into it and still double the costs. And it looks as though if we really wanted to beat the so-called bug, it would be best to have a catalyst, which when an asymmetric center was formed would direct the reaction to go and give you mostly the desired isomer. For this purpose, the 100% efficiencies that enzymes achieved would not be needed to have something of real value. this point in time, I was aware of extensive studies by Akabori in Japan, starting maybe in the mid-50s. He modified heterogeneous catalysts like uranium nickel and even palladium with chiral agents, but he never got anything high enough yields to be of any preparative interest. All these thoughts kind of remained fallow for several years. In the meantime, I became part of a program for doing exploratory work in industry. I was given a brand new PhD hiree to train for a period of 1 year before he went on to more pressing things. And industrial labs, they're always wrestling with the problem of doing undirected research. And this is just one of the many ways to achieve this goal. I'd been through several new employees on a number of projects, and I became aware of Professor Wilkinson's discovery of chloro, tris, triphenylphosphine, rhodium. This is 3 triphenylphosphines and a rhodium and a chloride. And this product had amazing properties as a soluble hydrogenation catalyst when applied to unhindered olefins. Homogeneous catalyst had been prepared before, but this was the first one that even compared in rates with the well-known heterogeneous counterparts. And a second development occurring just at about the same time in the mid-60s was the development of methods for making chiral phosphines by Mislow and also by Horner. Phosphorus, like carbon, is tetrahedral, and when 4 different substituents are attached, can exist in D and L forms. In the case of phosphines, the lone pair of electrons on the phosphorus counts as a substituent. Earlier, it was thought that phosphines might pyramidally invert like their nitrogen analogs, but Mislow and Horner showed that they were stable at room temperature. They turned out to have half-lives of maybe 115 degrees of maybe a couple of hours. And for our hydrogenations, this stability was quite adequate. Then our basic strategy would be to replace the 3 triphenylphosphines on Wilkinson's catalyst with a chiral phosphine and hydrogenate a prochiral olefin. That is an olefin that once it's hydrogenated, generates an asymmetric center. This experiment was performed on alpha phenylacrylic acid using the known methylpropylphenylphosphine, and we got an enantiomeric excess of 15%. Next. We took alpha phenylacrylic acid and hydrogenated it with 3 ligands, propyl, methyl, phenylphosphine, just like Wilkinson's, and we got hydrotropic acid, generated a new asymmetric center, and our enantiomeric excess was 15%. This is, of course, a no preparative value, but it did establish, this bias did establish that the hydrogen, the ligand, and the substrate were all on the rhodium at the same time. And furthermore, we established that this hydrogenation was accomplished totally in solution. It was not done by some extraneous rhodium plating out on our reactor. The inherent generality of this method was appealing to us. It offered almost unlimited opportunities for matching substrate and catalyst and moved toward the goal of achieving efficient results. Well, we were not alone in having this idea. I think we were the first to report on it. It was discussed, I think, in a question session at Wilkinson's lecture on his soluble hydrogenation catalyst at a Welch Foundation conference in Texas. Horner, shortly after our paper, reported even more modest results. He used the same methylpropylphenylphosphine and he hydrogenated a substituted styrene. There were others with other phosphines with all equally uninteresting results. And for some strange reason, we may have been the only ones naive enough to pursue this lead in depth. Actually, there was definitely nothing in the literature to encourage us to proceed further. And we proceeded, though, to make mechanistic study, and we did show there was an exact stoichiometry, that we didn't need 3 ligands, as in this structure. We only needed just 2 of these ligands with the rhodium. There was an exact stoichiometry here. And we went back and looked more at alpha-phenylacrylic and as a triethylamine salt. We got a little better results, but we never did do well with this system. And then while groping around this area, not really getting very far, another seemingly totally unrelated development appeared, which played an important role in our project. This was the discovery that a fairly massive dose of L-DOPA was useful in treating Parkinson's disease. And it's created a sudden demand for this rare amino acid. And because of Monsanto's special position, we were a manufacturer of vanillin, which provided the 3,4-hydroxy-diphenyl moiety. We found that they were custom manufacturing a racemic intermediate, which Hoffmann-LaRoche was resolving and deblocking L-DOPA. The synthesis followed closely the Erlenmeyer azelactone procedure described in organic syntheses, and went by way of a prochiral enamide, which is hydrogenated to block DOPA. Next. I'd like to say a little aside on secrecy here, that we learned about this manufacture from the usual corporate grapevine, and I talked to our lawyers about it. I said, well, what are they doing? And they said, oh, this is the most hush-hush secret thing. We signed all kinds of papers. We can't tell you a thing. Sorry, we won't do anything about it. And I happened to have a copy of Organic Syntheses on my desk, so I opened it up to, I think it was page 1, and said, well, by any chance, is this what they're doing? And the lawyer looked at this and said, you mean I signed all these secrecy agreements? This is exactly what they're doing. I signed all these secrecy agreements for something that's already in the public domain. And I said, well, evidently. And I think it's a lesson in human affairs, frequently the less you have to hide, the more secrecy you get. So, well, it turns out that this enamide offered us a golden opportunity. They were condensing vanillin aldehyde with the benzoyl glycine to give an enamide precursor. And this was hydrogenated to give a DL mixture, and they used a symmetrical catalyst of palladium on carbon. It's a very conventional system. And they got a racemic mixture, which was resolved. Actually, we sent this to Hoffmann-LaRoche, and they resolved this with an organic base, probably, and then deblocked it to L-DOPA. And they only cost 50% of what they wanted. And this offered a golden opportunity for us to try, since there was a hydrogenation here. We had this burgeoning hydrogenation process, and we could put in our chiral catalyst here. This would make a very nice commercial target. And we soon found that this enamide worked in our system even better than the simple olefins we'd been trying. And this was surprising because this was a more highly substituted olefin. And even here, we were not alone in this discovery. Others, right at about the same time, found out that these enamides offered particularly good substrates for the Wilkinson-type catalyst. But even so, we ran the asymmetric hydrogenation of this thing with our methylpropylphenyl phosphine, and we only got about 28% in anomeric efficiency, nothing good enough to be of any use. But the stage was beautifully set to run a structure versus activity study. First of all, we had a good test reaction. For this test reaction, next slide, please. Next. Test reaction, we used the phenylalanine intermediate because we had the good optical parameters and we could test what we'd done more easily. And in this test, we had the good test reaction, this phenylalanine hydrogenation, to give us the precursor of phenylalanine. And we also had a good test for efficiency. We would just run the hydrogenation, we'd dilute it to volume and stick it in a polarimeter and see how much rotation we got. And this is an interesting aside here because in modern times, one doesn't use a polarimeter, one uses a fancy chromatographic column, one runs it and then sticks a little bit on your column and it tells you how much D and how much L you got. And there was a very young guy in Monsanto, he must have been about 20, that came in and he's telling me he wanted to see me, and he first congratulated me, and he said, well, I'm running some chromatographic analyses for a pharmacy here, and I just want to know how you measured your chirality. And I said, well, very simply, I just diluted the volume and used a polarimeter. He said, they had one of those in those days. And then I had to explain to him that even Pasteur had a polarimeter. But now the job was to find a phosphine of the proper structure. We anticipated this might be a long, hard job, but we embarked on it. We felt in our bones that we were on the right track. Early on, we tried a number of phosphines, one with a chiral side chain. Didn't give us any interest at all. And then we used the usual variations. We took the methylpropylphenylphosphine and varied the propyl group to isopropyl and cyclohexyl. Still gotten low results, 28 to 32%. Then our final real variation was really not very ingenious, because we set out to introduce the ortho and acetyl group. This would provide some additional steric hindrance, and also had an ether linkage, which could provide a site for hydrogen bonding. It sounded interesting. And probably more important, the ether linkage would be stable to the Grignard chemistry we needed to make the phosphines. In those days, our group was a very small, cohesive group, and we were in continuous contact. What we decided to do was always arrived at by just informal consensus. We never held a meeting. I hate to admit it, it's much easier to invent with a small, underfunded group, and being kind of lean and hungry is quite conducive to invention. And, well, the first thing we made was methyl phenyl orthoanacylphosphine. This we call PAMP. And we immediately got EEs in the low 50s, and we got it by playing with conditions, got it up to 58%. This was very encouraging. And we looked at PAMP, and we found we could further modify this molecule by taking the phenyl group and hydrogenating it to cyclohexyl. And this gave us methyl cyclohexyl orthoanacylphosphine, CAMP. This change gave us immediately 80%, and then by juggling addition, we get up to 88. These results next. These are summarized in this slide. We started off with chirality in the side chain, barely got anything. We used a known methylpropylphenyl, got 28%. We varied it with isopropyl, got 28%. Cyclohexyl still got only 32%. And we put in the orthoanacetyl, got methyl, phenyl, orthoanacylphosphine. We were able to juggling to get up to 58%. And then we converted the phenyl by selective hydrogenation to cyclohexyl. We got orthoanacetyl, phenyl, CAMP, got 88%. Right. I hate to, it all seems sort of too easy and simple, but really, this is the first time ever, anywhere, that anyone had obtained enzyme-like selectivity with a man-made catalyst. Never in our wildest imagination did we think a structure versus activity study would converge so quickly to a product already with commercial potential. CAMP was our 6th candidate. And our next slide, please, next. CAMP was an exceedingly simple structure. Cyclohexyl, methyl, orthoanacylphosphine. By any stretch of the imagination, it was terribly simple. And look what it was doing. As I look back from this perspective, I don't even think that we were emotionally equipped to realize what we'd done. Here with the simplest of molecules, CAMP, we had solved one of the toughest synthetic problems. For the past 100 years, it had been almost axiomatic among organic chemists. If you want to get high yields, only nature's enzymes could ever do this job. And our patent department looked at this invention. They never really considered what our invention was. They just thought that use of chiral phosphines and rhodium was the invention. And of course, without finding PAMP or CAMP, we'd had only a new way of doing what had already been done before. And the lawyers felt that this was, our first result wasn't much, we realized, but that we could very easily come up with an improved embodiment. And in this, they were unusually precise, especially for lawyers. But I would not call this just an improved embodiment. I would say that CAMP was definitely a quantum leap. We've called these catalysts man-made. This isn't strictly true. We have not violated the general principle. If you want chiral molecules, you've got to get them with the assistance of previously formed natural products. Our isometry, of course, was obtained by the phosphine synthesis, where L-menthol was used to do the resolving. And the L-menthol, of course, comes naturally from peppermint oil. But a very small amount of L-menthol could create a very large amount of chiral product. Now, CAMP, of course, turned out to work very well, equally well, in the more complicated L-dopa precursor. It made no difference whether you used the mean blocking group was benzoyl or acetyl or anything else. And at this point, we were strongly motivated to develop a commercial L-dopa process. It's kind of a rare thing that the emergence of a substantial demand for a chemical is so closely timed with an invention for a new way of making it. Our management reluctantly increased our manpower, but didn't really believe we could do it until the hydrogenation was run on a 50-gallon scale without incident. And since CAMP was already good enough, we stopped exploring phosphines and concentrated on converting this unique hydrogenation to large-scale production. And this process was helped when another fortuitous event occurred. Monsanto decided to get out of their original product, saccharin, and an idle plant was now available for this kind of fine chemical manufacture. These things were then put together to give our simplified L-dopa process. And that's next, please. The simplified L-dopa process is still following the Erlenmeyer's lactone procedure. Vanillin was condensed with acetylglycine to give an azelactone, which was opened without isolation to water to give an enamide. And this enamide was now hydrogenated with two CAMP ligands to give only the L isomer, which was then deblocked to L-dopa. The novel step being the hydrogenation, of course. And it turns out that the chiral hydrogenation was by far the simplest step in this entire sequence. We were able to start with just a slurry of prochiral olefin in an alcohol-water mix, and we would hydrogenate, and we'd end up with a slurry of product, which we could filter off and leave behind the catalyst and the residual racemate in the mother liquor. At first, we used an in situ developed catalyst, but later we made a complex of rhodium and 1,5-cyclooctadiene with 2 ligands as a fluoroborate salt. And these catalysts were also very fast, and so that mole ratios of substrate to catalyst were about 20,000 to 1. Thus, even such a super expensive complex as we used was used at close to throwaway levels. It's interesting that this very fast reaction we didn't really discover till we ran on I hate to say it, a 1,000-gallon scale. The first 1,000-gallon run, we had our technical assistant, Bill Sherma, was supervising it, and I told him it's going to take 8, 10, 12 hours to finish the batch. But get it started, go out and get yourself a bite to eat, and you're going to have a long night of it. Well, he did that. He got the reaction started. He went out to eat, came back, and maybe an hour or two later, called me on the phone, said, "Trouble. The batch isn't taking up hydrogen. What do I do?" And I said, "Oh, gulp, that's real trouble." So I asked him to say, "Well, just analyze it and let's see how far we got. Then we'll figure out what to do." And so he analyzed it. We had a cute little UV analysis. So he called me back in half an hour and said, "It's done." So we'd gone about 5 times faster than we anticipated. This is the first time we'd done this in the lab and all the runs we'd made. It turned out that the reason for this was that here he was, for the first time, using a big trailer truck of hydrogen. And the hydrogen was purer than the stuff we had in the lab. It had no oxygen in it at all. The stuff in the lab, when you fill the cylinder, you can be a little sloppy and get some oxygen in the hydrogen. These catalysts don't catalyze the reaction between hydrogen and oxygen, and so that the oxygen stayed around to destroy a little of our catalysts. So all our lab runs had been sloppily done to date. And we went back and corrected this difficulty, and we found we too could operate then at 20,000 to 1 in 8, 10, 12-hour cycle. And another thing is, process was carried on by production we never had any trouble with the hydrogenation. The usual troubles, little crystallinity problems and so forth, and the other steps. But we never got any midnight calls on the hydrogenation. They'd gone on for, I don't know, 5, 8 years. And I was talking to one of our production people, and he said, well, I've just been to a party. We were celebrating our millionth pound of L-dopa that we made. And obviously, you know who wasn't invited. So, but that's these plant people, I don't think, ever realized that they were operating a totally unique kind of process that had never been done before. I think because it went so smoothly. But I want to put an aside on this that even in the best case, we make some racemic mixture, and this must be separated. In this case, we put this in the mother liquor. This separation is kind of easy or hard, depending on the nature of the racemate. If the racemic modification has a different crystalline form than either D or L, the separation nanobrew will be inefficient. One achieves, say, 90% EE. One can't get out easily more than 75 or 80%. And at lower efficiencies, your losses are excessive. And for such a system, we need a catalyst of very high efficiency. And unfortunately, most compounds are this type. If, on the other hand, the racemic modification is a conglomerate, which have an equal mix of D and L crystals, then recovery of excess L can be achieved with no losses. Here, you'd have a 90% EE, will give you 90% recovery easily. And fortunately, our L-dopa process, the intermediate, is such a conglomerate, and the separations are efficient. This lucky break was most welcome for us. And if one thinks back, ours was the same luck Pasteur had 150 years ago in his classical tartaric separations. You know, at the time of our initial commercialization, we were running at 50-gallon scale then. We learned of a new ligand developed by Professor Kagan in France, and he called it diop. This was a chelating bisphosphine made from tartaric acid, and here the chirality was totally in the chiral backbone, not on the phosphorus. But he got results pretty comparable with CAMP. And we had always hypothesized to get good results, one needed chirality directly on the phosphorus atom. Made sense. This is where the action is. But Professor Kagan showed us to be totally wrong. It's most appropriate. This invention using tartaric acid should have come from a Frenchman in the land, Louis Pasteur, who, of course, was the one that got this whole field started. But the bisphosphines have become the wave of the future, kind of a lot of asymmetric catalysts that have been developed since. And shortly after, we came up with our own bisphosphine by dimerizing PAMP using another Mislow procedure. We called it dipamp, and where chirality still remained on the phosphorus. Next, please. So that's diop. I forgot to, that's Kagan's diop. And then the next slide, next. This is our dipamp, which is just 2 moles of methyl ornithoinosine phenylphosphine tied together through the methyl groups. And it got 95% EE. And we immediately switched our commercial process over to use it. And part of our motivation was the quick, it was easier to make DIPAMP than it was CAMP. And it was also a very nice crystalline, air-stable solid rather than an air-labeled liquid. And actually, when we started this, work, we expected that there'd be a very high specificity required between substrate and ligand, just like enzymes. And generally in our hands, the hands of those that followed, a good candidate, however, has been useful for a wide range of applications. This feature has been substantially enhanced their value in synthesis. It looks out that these chiral hydrogenations applied to enamides are entirely general, especially with DIPAMP. Next, please. If we take the general case, R can be almost any group here, and we can still get a high nanomeric efficiency. I think I left the hydrogen off there. I just noticed that. And another thing I wanted to point out, this works only well with Z enamides. This, you can have cis-trans isomerization of this R, and this H can be interchanged. The E series do not work as well, but fortunately for us, the base condensations used to make these compounds give only the Z form. So we can get all kinds of results here. If R happens to be carboxyl, you can understand that these two catalysts get confused, and we cannot do the aspartic case. That is still better done with enzymes. This generality then applies to practically all the known amino acids, which at least in principle can be obtained from a similar enamide precursor. And I think evidently the polar carboxyl enamide overwhelm any variation in our group. Again, Lady Luck was with us because if we had had a choice where our catalyst would be useful, we couldn't have selected a more important area than the alpha amino acid building blocks of our proteins. And some of the more important ones are listed next. There's 5 or so important ones, all giving high EEs, and our colleagues at Hoffman LaRoche ran maybe even a dozen more in the aliphatic series, all using DIPAMP and all getting high EEs. And this generality can be extended to other things in enamides as long as we have the ability to chelate. The next slide, please. The amines, the enamides work because they can chelate with the rhodium. This NH can be replaced by oxygen to give enol esters. These work well with all kinds of variations. And the oxygen can be replaced by methylene to get an itaconic. We also get highly efficient results. So we can get a tremendous number of compounds available that can be made this way. But one system which did not work well was our original model, alpha phenyl acrylic acid. And this is an important area because these alpha aryl propionic acids that you make from this are important as non-steroidal anti-arthritics like Advil and ibuprofen and Aleve and so forth. And usual case here, only one enantiomer is active. And so this is a very valuable commercial target. We tried hard to solve this problem. We even got to use ruthenium ligand systems and so forth. But it took Professor Noyori with his binap ruthenium to actually solve this problem. And I'm afraid this is just another example in the history of invention. The one who makes the first discovery seldom makes the second. And a grander stage, one might explain why there are so few Nobel laureate repeats. And soon after the appearance of DIOP and DIPAMP, a considerable number of bisphosphenes with chiral carbon backbones were found. These were all came out in the 70s. Next slide, please. These just show this is just a small sampling. There's a great many ways to solve this same problem. The first one, Bosnich's, are rather simple. and it only had methyl and hydrogen in the chiral center, and even one chiral center would work. This is a little more elaborate with ferrocene. The Achieva one was very fast, fastest one we have ever looked at, but it gave D amino acids from natural hydroxyproline, and to get these two centers inverted to give L amino acids is rather complex. The Rhone-Planck was a diop variant. The final one was very easy to make. I was able to make this one from the back of the envelope directions. I learned it from Giango in a bar in Corpus Christi. Have it in a week. But these are limited in that the phosphorus-nitrogen bond solvolizes slowly, and therefore you lose your catalyst unless you get an exotic solvent like tetrahydrofuran, which is not too useful. And it's interesting that over the years, we made a lot of chiral phosphines, but we never good one without our beloved ortho-anosine group. And others have used it in connection with their bisphosphines, like these and a whole bunch. They get no particular advantage. Thus, choosing suitable structures is still pretty much guesswork. In our hands, dipamp was by far the most versatile and remained supreme for many years. Later in the 90s, an improved bisphosphine was reported by Burke, working at DuPont. Next, please. Next. This was a phosphylane type of material where R was methyl or ethyl, and he called it DuPhos. And it got 99% EE, really approaching enzymes. And since Burke's day, there are others who have reported the 99, 98% EEs, and a number of other ones. And these were supposed to go also quite fast, 20,000, 10,000 to 1. And these high EEs can be important. Remember, the racemate is not a conglomerate. I'd like to say a few words on the phosphines. Next, please. We made our phosphines from trimethylphosphite reacting with ortho-N-acyl magnesium chloride. We got a phosphonite in, immediately rearranged it with our Bootsoff rearrangement. We ended up with a phosphinic acid and reacted this with L-menthol. The main thing here is that the L-menthol gave us a pretty good asymmetric synthesis in that we got 80% of the one we wanted, only 20% of the one we didn't want. Next slide. We took that menthol ester that we wanted and reacted with phenylmagnesium chloride, and that would give us PAMP, which we'd selectively hydrogenate to get the phosphine oxide and then reduce it to the phosphine. That would be CAMP, our CAMP. And then if we took this and coupled it, we made a lithium derivative with lithium diisopropyl amide, reacted with copper-2. You give a dimer, and that was the dipamp oxide, and reduce it with trichlorosilane to give RR dipamp. This just gives you an outline of how we made the phosphine. We do this, they were expensive chemicals, but we get them cheaper, making a 10-year supply in a couple of plant batches. But now we had the phosphines and the ability to use them commercially. We'd like to know a little bit how they were working. First of all, when one makes energy calculations, to get 90% EE, you're only talking about 2 kilocalories difference in energy. And this is just about the same thing as in the rotation barrier in ethane. So extremely sensitive things may happen to cause these things. And we're probably not going to be able to predict very well, but we like to always take a crack at it. And we decided we'd do some X-ray crystal structures of our catalyst intermediate, the precursor. The next slide, please. This is the solid intermediate that we add in the catalysis. It's a fluoroborate salt with cyclooctadiene and rhodium. It's what we call a square planar complex. The rhodium is, in a planar sense, to 4 different groups. And we wanted to run an X-ray structure of this and see how the phenyl groups were oriented. And For this purpose, I've vastly simplified the X-ray structure. I've left off the fluoroboride, I've left off the COD, and I've used a little artistic connection, phenyl rings, so it looks a little easier. And next slide, please. Let's look at RR dipamp. 2 of the rings are face exposed, and 2 of them are edge exposed. And the ones that are face exposed contain the ortho-anecyl group and what I call the skewed methylene. That's the 5-membered ring that's back. There's 1 methylene's above the ring and 1's below the ring. And you can just speculate that a possible bulky substrate would lie more easily along the face-exposed rings than the edge-exposed rings. And from this, we could make a prediction. From the chirality of the phosphine, we could predict what the chirality of the amino acid you get. And RR dipamp, as predicted, would give S amino acids. Now, this is not much of a prediction because you have 50% chance of being right anyhow. But we started to apply other systems. Excuse me, well, I only got 2 minutes left. So we applied it to these other systems, and we're also able to predict. And when one does that, it gains credibility. But then Halpin came along and isolated an intermediate, which he showed that the intermediate lied along the edge-exposed ring. And so our theory probably was wrong, but anyhow, it was able to predict for the right reasons. So I think I better conclude this, giving me the time up. And including comments, I would say we got these soluble catalysts. They will continue to be used in industry wherever the enamide is available easily, but the biochemical routes are often come out quite simpler. And one area where they will be useful is making D amino acids, and not where you won't have biochemical routes. And then finally, I think the most important use will be as a labor-saving device in the laboratory for making available a large number of chiral compounds where the chemist doesn't have to perform laborious resolutions. And for such an invention to succeed, I've talked about an invention. For an invention to succeed, Paul Ehrlich, the father of chemotherapy, has always said that you require 4 Gs. Next, please. Next. Geist, Geld, Geduld, and Gluck. The first of these Gs is obvious. You've got to have a good idea. The second is you need to have financial support. And for this, there must be a balance. Not too much or too little is inhibitory. I have a Peter Rano cartoon which illustrates this point. Next, please. And now I'm off, and I'm taking with it only the bare necessities of life. In our research safaris, we should only go with the bare necessities. Now, 22 back to 4G. Next, please. Next. And the third one of these, I'm sorry, well, you got my 2 associates. I guess I got too far. Can you back up one? The third one of these, you've got to have patience, and things never move as fast. And the fourth, you've got to have luck. And I don't think any invention should ever be made without some fortuitous event helping out. In our case, I think we had a longer lucky streak, and we may have even set a record than most people. And then I wanted to point out my 2 associates. Next slide. Jerry Sabicki on the left, and Billy Vineyard on the right. Without, this has been always very much of a joint enterprise. And in conclusion, I'd like to add a couple of Gs to the Ehrlich's list. I'd say we're extremely grateful to have so great an honor bestowed on us by your committee. Thank you.